Improved seam carving for video resizing. Seam carving is an effective technique for content-aware image retargeting. By removing or inserting seams from an image, it can be changed to fit a given size. Multi-size images also enable interactive size change. In a similar manner, videos should be allowed to change size dynamically, but cropping or scaling do not perform well. One possibility is to apply seam carving to each video frame independently. However, the results of such an approach are often very jittery. In some simple cases, we can search for regions on the image that are of low importance in all video frames. We take the maximum energy projection in all frames and use it to carve the same set of seams from all the frames. We can now retarget videos to a given size using seam removal or insertion as in images. We can also define multi-size videos that interactively change their size. Nevertheless, in other examples, removing the same set of seams in all frames can create serious artifacts in the resulting video. It is clear that seams must be allowed to adapt and change over time. Our solution is to treat all the video as a 3D cube. We then replace the dynamic programming algorithm that is limited to 2D with a 3D graph cut approach. We define a grid-like graph whose nodes represent pixels and add a source and target virtual nodes on both sides of the cube. A cut in this graph defines a surface seam inside the space-time volume. The intersection of this 2D surface with each frame defines the seam path on that frame. Our construction guarantees that the seams would be monotonic and connected. Here you can see a comparison of video resizing using fixed seams and adaptive seams. Although the results are better, some artifacts are still noticeable. In another example of video retargeting, notice how the seams damage the sync rim and Remy's figure. In fact, these artifacts can also be found when resizing just one frame of the video. They also return in other static image examples, using the original seam carving operator. By examining seam removal closely, we find that in some pixels the image energy is increased because new edges are created. We find that when removing some seams, more energy is inserted to the image than removed. In our new approach, instead of looking backwards, we look forward at image edges that are created when the seam is removed. We remove seams that insert the least amount of energy to the image after their removal. We found that in most cases, using forward energy gives better results than using backward energy. It also provides better quality results for video retargeting. We show several examples of video retargeting using seam carving. Our first examples use the forward energy to change the aspect ratio by reducing or enlarging the video. We can also combine high-level information such as face detectors or saliency maps with the forward energy. In this example, we use the motion saliency from Wolf et al. By storing the seam order, we can also define multi-size videos to dynamically change aspect ratio. In this example, you can see a comparison of scaling, cropping, and seam carving for resizing video. Using negative weights, we can also remove objects from a video scene. We thank you for your attention.